Okay, I am now recording. Okay, so this is I'm now recording. This is lesson 25, major reminders. The final for this class, Math 241, is on December 21st from 6:15 p.m. to 8:15 p.m. The second exam is on December 9th, and review for the second exam is on December 7th during class. Second exam is also during class. Also, another announcement, the last office hour next week has been moved to Wednesday, December 8th from 6:45 p.m. to 7:45 p.m. so that I can help you if you need it for the second exam. Okay. So if you have questions about the second exam, I can answer them December 8th from 6:45 p.m. to 7:45 p.m. during that office hour. Okay, so the office hour this week is still at its usual time on Friday. You can see the times of the remaining office hours on Blackboard Collaborate Ultra on the course website on Blackboard. Okay, so those are all the announcements. The homework due today was homework 9, those two sections, and homework 10. Are there any questions about any of those problems?
Yes, homework 10, section 6.9.2. Could you just go over number 2, please?
Sure. 6.9.2, number 2, right?
Yes.
Okay, so 6.9.2, number 2. If families are selected at, is this on your screen? Can you see it? Yeah, okay. So if families are selected at random from a certain densely populated area, their annual income can be treated as a normally distributed random variable with mean mu equals $10,000 and standard deviation sigma equals $2,000. Oh, okay. I guess there was a typo. I didn't write the question, right? I gave the information without the question there. Okay, let me copy this and bring this to Word. Okay, so here's the question. So at the end, I should have written something like, what is the probability that that a family has an annual income of, let's say, at least $12,000. Okay. So I guess it was just a matter of, okay, I didn't write in that last part there. Okay, so let me answer this question. Okay, so okay, so what is the probability that a family has an annual income of at least $12,000? So the standard deviation is sigma equals 2,000 and the mean is 10,000, right? So the probability so let's let X equal to the annual income of the family, okay, in that area. The final is on December 21st from 6:15 p.m. to 8:15 p.m. So this is all in the, you can see this also on Blackboard when I post the lessons. Okay, so let X equal the annual income of a family. And so we want the probability that the annual income is greater than or equal to 12,000. And so that's equal to the probability okay, so let X equal the annual income of the family. So if you think about the random variable Y, which is equal to X minus mu over sigma, then this is equal to x minus 10,000 divided by 2,000. Okay. So the probability that x is greater than 12,000 is the probability that x minus 10,000 divided by 2,000 is greater than or equal to the number 12,000 minus 10,000 divided by 2,000. So I'm just expressing the same inequality with an equivalent one. The x's that satisfy this one are the same as the x's that satisfy this one, because I'm just subtracting by 10,000 and then dividing by 2,000. And so again, I chose those numbers because x minus 10,000 over 2,000 is y, as I defined it, and that's greater than or equal to 1, because 12,000 minus 10,000 is 2,000, divided by 2,000 is 1. Now here, y is a standard normal random variable, right? Because we talked about how if you take a normal random variable, subtract its mean, and divide by sigma, the standard deviation, the result is a new random variable, which is a standard normal random variable. So this y is a standard normal random variable, and this original probability is equal to the probability that y is greater than or equal to 1. And so this is equal to 1 minus the probability that y is less than 1. And so you just need to translate this into the probabilities in the table we have. So this is 1 minus the probability that y is less than 0, plus the probability that 0 is less than y less than 1. And this is equal to, so this is equal to 1 minus bracket. Probably y is less than 0 because y is a standard normal random variable. This is 1/2, because y has mu equal to 0 as the mean. So half of the area is to the left, half is to the right. And so this is plus still the probability that 0 is less than y, less than 1. Okay. So this is equal to 1/2 minus the probability that 0 is less than y, less than 1. Okay, and so now we have that the probability that x is greater than or equal to 12,000 is equal to 1 minus that probability. Okay, and so if you use the table, let me put the table on the screen. Okay, so what we need is just the probability y is less than 1. So here's 1, 0 less than y less than 1, where y is standard normal random variable. So that's 0.3413. 0.3413. Okay, so that's 0.3413. Okay, so it's 0.5, which is 1/2, minus 0.3413, which is equal to 0.1587. Because then it's 15 and then 49, and that's it. Okay, does that help clarify that? Does that make sense?
Yeah.
Okay, so then that shows you how to do that kind of a problem. Okay, so then you're applying this idea, but just to a word problem. Any other questions?
Really quickly, the next one, 6.10.2, number 1.
6.10.2, number 1. Okay, 6.10.2, number 1. 6.10.2, number 1. How might you estimate the average income of residents of a very large city without finding the income of every resident? What theorem may be used to justify this method? So the method, so the theorem you would use would be the strong law of large numbers. Okay, so by the strong law of large numbers, that means that, right, so since you're in a very large city, there is a lot of residents, right? And so if you want to find the average over a very large number, right, over a very large sample size, then that means that eventually, if you take the average, it's eventually very close to the mean. Okay, so the strong law of large numbers would tell you that the probability that the average is very close to the mean is very close to 1. Okay, so since n is large, with great probability, the average is very close to the mean. Okay, so the solution would be to find the mean, of the random variable x, which is the average income of residents. And so then, okay, so you would just, okay, so let me go on here. Okay, so then for this one, you would just take the average, income of each of a large number of residents, find the average of them, meaning add the incomes of n residents and divide by n. That would approximate the mean, slash often called average. That would approximate the mean with great probability by the strong law of large numbers. That makes sense?
Yes.
Okay, so the strong law of large numbers says that if x is a random variable, and x of I is the ith observed value of x, then if you take the sum of those x values, so if you take the sum from I equals 1 to n of x of I and divide it by n, that this is approximately mu, with great probability if little n is large. Okay, so since little n is large, you calculate this for a large value of n, and it's approximately the mean with great probability. Okay, any other questions about the homework? Okay, good. Okay, so let's continue with the next lesson. Okay, so we are now on 7.2.2, which is on multivariate cumulative distribution functions. Okay, definition 7.2. The multivariate cumulative distribution function of random variables x1 to xn is the function capital F defined by capital F x1 to xn which is equal to the probability that x1 is less or equal to x1, x2 is less or equal to x2, dot, 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 xn is less or equal to xn for values negative infinity less than x of I less than infinity, I from 1 to n. So I don't know what you mean by the formula, right? So do you mean that what the strong law of large numbers, this form, this thing? You need to know the strong law of large numbers. So you need to know this statement. Okay, so you need to know that. So you need to know that approximation.
So I meant like in general, do we have to memorize the order formulas like in top of the head, like
Which ones?
like order general formulas? Do we have to memorize them like for exams, or just like understand the like how to use them?
You need to be able to justify the reasons for your answers, right? So if the reason for your answer is a certain equation or something, you need to know it, right? So you need to be able to formulate a proof of the answer, not just the answer, but the reason for it.
Okay.
So so it depends on the question. But
Okay.
okay, you get it. Okay. Okay, so definition 7.2. So I've written it out. The multivariate cumulative distribution function of the random variables x1 to xn is a function capital F defined by that equation. So it's equal to the probability that each of the capital X's are those corresponding little x values. Okay, so it's a probability that capital X1 is less or equal to little x1, and capital X2 is less or equal to little x2, and ... and capital Xn is less or equal to little xn. Okay, and this is for any assignment of values little x sub I that are real numbers. Okay, so for each assignment of real numbers little x1 to little xn, capital F of that n tuple is equal to this probability. Okay, and so that's the multivariate cumulative distribution function of the random variables capital X1 to capital Xn. Okay, if two random variables are involved, then that function, the multivariate cumulative distribution function, is called the joint cumulative distribution function. Okay, so this is an example. Consider the random variables capital X and capital Y of example 7.3. Okay, find capital F of 2, 1. Okay, so capital F of 2, 1 is equal to the probability that capital X is less or equal to 2 and capital Y is less or equal to 1. And so that's equal to little f of 2, 1 plus little f of 2, 0 plus little f of 1, 1 plus little f of 1, 0. So the example that we're referring to here, example 7.3, in our previous lesson, we had example 7.3, right? So here we had this table, right, that said we had a joint probability function, probability that x is equal to a value and y equal value given by this table, the different values of x and y. And so saying that, so I'm going to copy this table and then refer to it. Okay. So let's go over here. So it's given by these tables. So we want capital F of 2, 1. It's equal to the probability that capital X is less or equal to 2 and capital Y is less or equal to 1. So these are the 4 ways in which that happens. So here, I'm just going to bring this back black. So if X is 2 and Y is 1, right, then that falls in those range of values. If X is 2 and Y is 0, that also does. If X is 1 and Y is 1, that also does. And if X is 1 and Y is 0, that's another possible value. And then the other ones are plus F of 0, 1 plus F of 0, 0. So 0, 1 would be this, have this probability, and 0, 0 would have that probability. So these are all the possible values of x and y in that example, where x is at most 2 and y is at most 1. So you just add those separate probabilities. So this is equal to 0.05 plus 0.11 plus 0.11 plus 0.23 plus 0.11 plus 0.23. And that's equal to, when you add them up, that's equal to 0.84. Okay, so that's the probability that x is the most 2 and y is the most 1, or capital F of 2, 1. So this is an example of calculating the value of a multivariate cumulative distribution function of random variables x1, x2, where instead of x1, x2, it's x and y, 2 of them. Okay, any questions about that? Okay, so the next thing is on the multivariate probability density function. Okay, so this is definition 7.3. Continuous random variables x1, xn are jointly continuous if there is an integrable function little f such that the probability x1, probably the x1 is at most little x1 and x2 is at most little x2 dot, 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 and xn is at most little xn is equal to the integral dot, 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 a bunch of integrals. So let me write this down. T1, T2, dot, 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 comma, n, dt1, 2, dot, 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 etn, negative infinity to x1, negative infinity x2, dot, 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 negative infinity xn. Okay, so continuous random variables x1 to xn are jointly continuous if there is an integrable function f, little f, such that that equality holds. And this is for negative infinity less than x sub I less than infinity, where I changes from 1 to n. Okay, the function little f is the multivariate probability density function of the random variables. Okay, so when 2 continuous random variables are involved, multivariate probability density function is called the joint probability density function of the random variables. Okay, so we have those definitions. Okay, so some important facts. Okay, so by definition 7.3 above, if x and y are jointly continuous random variables with joint probability density function f of x comma y, then 1, the joint cumulative distribution function of x and y is capital F of x comma y, which is equal to is equal to this. So it's equal to f negative infinity to y, negative infinity to x, f of s comma t, yes, dt. This is for negative infinity less than x less than infinity, and both x and y are any real number. Okay, so the joint cumulative distribution function of x and y can be defined by this equation. Okay, so this is your joint probability density function, little f, and you're integrating it from negative infinity to x and then negative infinity to y. This is the probability that capital X is at most little x, and y, capital Y is at most little y. Okay, so for values a1 less than x less than b1 and a2 less than y less than b2, the probability that a1 is less than x less than b1 and a2 is less than y less than b2 is equal to the integral, the double integral of f of x comma y dx dy, where x ranges from a1 to b1 and y ranges from a2 b2. Okay, the third fact, if C is a region of points x comma y in the plane, and the probability that x comma y is in the set C, so that denotes the probability that the random variables x and y will take on the respective values little x and little y, so that the ordered pair little x comma little y is a point in capital C, then the probability that x comma y is in C is equal to the double integral over C of f of x comma y dx dy. So the integration is over region C, and the probability is only defined if the integral exists. Okay, so if the integral doesn't exist, the probability is undefined. Fourth fact is if capital F of x comma y is the cumulative distribution function of x and y, and the joint probability density function is given by f of x comma y is equal to f of x comma y is equal to d2 f capital F of x comma y dx dy. Okay. And so this is at all values x and y, where the partial derivative is defined. So at values x, y, where the partial derivatives do not exist, values for f may be arbitrarily assigned. Okay, so there are certain points in which the value of little f does not matter. Okay, and so at those points you can arbitrarily define little f. Okay, in order to talk about what capital F is. So to define capital F, well, no, okay, so it's saying what little f is. So that you use little f, but at all values x and y with partial derivative, for values of x and y where the partial derivatives does not exist, where you cannot calculate this value, then you can give little f any value you want, and little f works when calculating probabilities. It doesn't matter. Okay. Okay. So these four statements can be extended to more than two jointly continuous random variables. Okay. So we're talking about two here, but you can talk about these statements when your function has more than two random variables in it. Okay. So example 7.7. Suppose x and y are continuous random variables with joint probability density function. Little f of x comma y is equal to is equal to 1/2 x e to the negative y for 0 less than x less than 2 and y positive, and 0 elsewhere. Okay. Part A, find the joint cumulative distribution function of x and y. Okay, so we have to split this up into cases. So case 1 is for only x values that are non-positive. So this is for x less than or equal to 0 and for any y. Okay, so for case 1, we only consider those values of x and y. So we have capital F of x comma y, which is equal to this. Okay, and so then this is equal to so this is our PDF here. Yeah. So this is little f defined. Now, if x is less than or equal to 0, then it's not in this range, because this is only for x between 0 and 2. And so the value of little f of these x's has to be 0. So that means that the integrand is 0. And so that means that this is the integrand. This is the double integral of 0. And so that equals 0. Okay, so that's case 1. Case 2 is for now in a new range, new values, 0 less than x less than 2, and y is positive. Okay. So here we have capital F again. And so now if x is between 0 and 2 and y is positive, that means that the integrand function little f is equal to this expression. Right? So we have this integral but we now have that little f there is this. Okay, so it's this, except instead of x, it's s, instead of y, it's t, right? Because s and t are dummy variables for x and y, respectively. Okay, and so now you just calculate this. And so this is then equal to, so you can separate the terms with s and with t. So you can think of this as a product of two integrals. So in your first integral, if you think about t's, you have from 0 to y of e to the negative t dt. And then for the x's, you have the integral from 0 to x of 1/2 s ds. Okay, so here's my integrand, right? You have an s and you have s and you have negative e to negative t. So I can move the 1/2 s to the integral for just the s here, right? And I can move the e to negative t here. Now, before I had integral from negative infinity to x, negative infinity to y. But if you look at t, right? T is representing y. And so that means that, right, so that means that y is only, this function little f is only non-zero for y positive. And so you don't care about the values of t for less than 0. So the only range you care about is from 0 to x. And x is between 0 and 2. And so you're stopping at a point in this interval. That's for s. And so for t, it's a dummy variable for x. And so x only matters for 0 to 2. So you only start at 0. You only start at 0 and you end at x. Okay. Okay, so here for y is strictly positive. And so t corresponds with y. And so you're starting at 0 and you're ending at the y value, which is positive. Okay, so then you have those two integrals. And so when you compute each of them, you get 1/4 x squared times 1 minus e to the negative y. Okay, this 1/4 x squared is for this integral, and then the 1 minus e negative y is for that one. Okay, and so then that's the value. So capital F of x, y is equal to this if x is between 0 and 2 and y is positive. The third case, case 3, is for, let's say you have negative infinity less than x less than infinity, and you have y is less than or equal to 0. Okay, so in this situation, here's your capital F. Okay, but little f, when y is less than or equal to 0, is 0. And so since y is less than or equal to 0, y is not positive, and so it does not fall in the top category, equals in the bottom one. So little f is equal to 0 there. And so that means that this expression now has an integrand of 0. And so now you're taking the double integral over the integrand 0, which means that the value is 0. This equals 0. Okay, so that's case 3. And then case 4 is, this is for when x is greater than or equal to 2 and y is positive. Okay, for x greater than or equal to 2 and y positive. So if x is greater than or equal to 2, we have this capital F here. And so now this is equal to, so now, okay, so you're going to have this integral again. So you have this expression. But this expression you only care about for, it's from negative infinity to x, but because x is greater than or equal to 2, the cutoff is at 2. So now you only care about from 0 to 2, because you're going you're starting at 0 and you're ending at x. But if x is greater than 2, you're going from 0 to 2. And if y is positive, you want to start at 0. Because that's all that matters is when y is positive, and go from 0 to y. And so those are your limits of integration there. And that's your integrand for when little f is non-zero. And so now you split this up into, again, the product of two double integrals, except now it's from 0 to 2, because the integrand limits for t are from 0 to y, and for s, it's from 0 to 2. So now you calculate each of those, and so you get 1 minus e to the negative y. Okay, and so the value of this is 1, so you get s squared over 2, so you get 1. The value of this is 1. And so you calculate that, you get 1, you get this is 1 minus e negative y times 1, which is 1 minus e negative y. Okay, so each of the 4 cases, we have the value of capital F of x comma y. And the 4 cases exhaust all possible values of x comma y. Okay, they're separate. There's no intersection between these 4 cases, and combined, the 4 of them exhaust all possible values of x comma y. And so now, as a conclusion, we could then say what capital F is everywhere, every value, little x and little y. So capital F of x comma y is equal to 0 for x less or equal to 0, and when negative infinity is less than y less than infinity. Okay, it has another value of 0, but I just separated so that you can follow what I'm doing. It's also 0 x for any x in which y is non-positive, y is less or equal to 0. Okay, so this was case 3, right? So this one was case 3, and so that corresponds with this one here. Okay, this is when x is less or equal to 0 and any y. And so that's this one. Okay, so case 1, this was case 3. The other possible values are 1/4 times x squared times 1 minus e to the negative y. And this is for the other value. So for when 0 is less than x less than 2, and y is positive. So the comma means and, not one or the other. And so this restriction of x and y, I'm going to label this as blue. And so this is case 2. I'm going to put this whole thing in the color just to accentuate the difference. Okay, and then the last one is case 4. And so that value is 1 minus e to the negative y. And this is for x greater or equal to 2 and y positive. And so these values denote by darker red, maroon of case 4. Okay, this was okay. All right, so for each of the 4 cases, you have different disjoint subsets x comma y, and capital F was defined there. Okay, so now we have capital F x comma y defined for every x comma y. Okay, and so that is the answer to A, finding the joint cumulative distribution function of x and y. So for part B, you want to find probability that x is at most 1 and y is at most 2. And the probability that 1 is less or equal to x, less or equal to 2, and 3 is less than y, which is less than or equal to 4. Okay, so the probability that x is at most 1 and y is at most 2 is capital F of 1, comma 2. Right? So capital F of 1, comma 2, looking at this, capital F of 1, comma 2, x is 1 and y is 2. So you can see that this belongs to the blue part. So this is for the blue region, capital F of 1, comma 2. X is any real x, and y is greater than 0. So we have a value in the blue region. Okay, and so that's equal to the value of this when x is 1 and y is 2. Okay, so the value of this when x is 1 and y is 2, so that means that here you have a 1 for x, and here you have a 2 for y. And so this is equal to 1/4 times 1 minus e to the negative 2. Okay, and so that's the answer to that one. And then the other one is the probability that 1 is less or equal to x, less or equal to 2, and 3 is less or equal to y, less or equal to 4. Okay, so this is just equal to double integral of little f of x comma y dx dy as x goes from 1 to 2 and y goes from 3 to 4. Okay, and so this is equal to, so if x is going from 1 to 2 and y is going from 3 to 4. So if x is going from 1 to 2 and y is going from 3 to 4, you're looking at these values, right? And so this thing corresponds with this one. So capital F of x comma y there is equal to sorry. X is from 1 to 2 and y is from, no, that's not. It's the blue one. So it's the blue region. Okay. So this is the blue part. X is from 1 to 2 and y is from 3 to 4. So x is between 1 and 2 and y is positive. So that tells you that the little f is equal to this function here. So we have this. And so now we have this thing right here. That's little f. Okay. So that's little f. There. And so now you just have to calculate that integral. Okay, and so when you calculate that integral, you get 3/4 times e to the negative 3 minus e to the negative 4. And then that's the answer to part B. Okay. Next example is example 7.8. Let x and y be continuous random variables with joint probability density function. Little f of x comma y is equal to the following. 2xy plus 3/2 y squared. This is for 0 less than x less than 1, and 0 less than y less than 1. And it's 0 everywhere else. Okay, so we have that function. Let capital C be the region of points x comma y in the plane such that x plus y is strictly less than 1. Find the probability that x comma y is in C. Okay. Okay, so let's look at a picture first. So I'm on this next page. Okay, so let's look at a picture. So you have the x-axis, you have the y-axis. Now we have this region between x between 0 and 1, and y between 0 and 1. So we care about is this region here. Okay, so then, so if you have the line x plus y is less than 1, so we have x plus y equals to 1, right? So x plus y equals to 1 is equivalent to y equals 1 minus x, which is y equals negative x moved up by 1. And so we have that the part of that line is this red thing here. This is y equals 1 minus x. Okay. This is y equals 1 minus x. And then if you want to talk about x plus y less than 1, x plus y less than 1 is equivalent to y less than 1 minus x. And so those would be these values here. In the blue section, in the blue square, it would be that pink region. Okay, so so this is the blue square here. It has the x-axis, the y-axis, and that other part. Okay, so our PDF little f of x comma y is only non-zero in this blue square. Right, so little f of x comma y, little f of x comma y is only non-zero in the blue square. Okay, and so the region C is the region of points here. So the region C is that region there inside of the blue thing, right? So the region C actually takes up more, but the rest of region C doesn't matter, right? The rest of region C is outside of the blue square, and because little f of x comma y is 0 there, we only care about the part that's in the blue rectangle. Okay, so we want to find the probability. We want to find the probability that x comma y is in the region C. Okay, and that boils down to finding the probability that x comma y is a point in the triangle, in the purple triangle in the blue square. Okay, so this is going to equal to the double integral over that purple triangle of f of x comma y. Dx dy. Okay, so it's over this purple triangle. pink triangle. It's over this thing. Like that part. Okay. And so to integrate that, it's just equal to the double integral. And little f there is 2xy plus 3/2 y squared. So this is dx dy of that. And now if we're taking the double integral over that triangle, it's the same as, well, you can take, if you're integrating, you can think of a vertical rectangle here. And so you can think of this as integrating from 0 to 1 minus y. Okay, so I wrote y equals 1 minus x. You can tell this thing because x equals 1 minus y. So then the height of this triangle, the height of this rectangle is okay. It's a horizontal rectangle, sorry. So we have a horizontal rectangle here. There we go. Okay, so you're integrating, and so your horizontal rectangle, so x equals 1 minus y. And so if you fix x, you're integrating from 0 to 1 minus y. And then that rectangle will sweep from x equals 0. So from y equals 0 to y equals 1. Okay. Okay, so x is going from 0 to 1 minus y. And then that's the height of the rectangle, which is horizontal. The horizontal length of that green rectangle is going from x equals 0 to x equals 1 minus y. And then it's sweeping from y equals 0 to y equals 1. And so you integrate that, and the number you get is 5/24. Okay, so this is equal to 5/24. Okay, so again, the probability that a point x, y is in this region C, the purple region C, where f of x, y is only non-zero inside the blue square, is equal to the double integral of little f of x, y, which is 2xy plus 3/2 y squared in the blue square, integrating over the triangle part. And so that's the integral from 0 to 1 minus y with respect to x, and then 0 to 1 with respect to y. And when you calculate that, you get 5/24. Okay. Any questions about how you visualize this? I'll calculate this integral for you, but just the reasoning here. Any questions? Okay, so on the Word, I'm just going to calculate. Okay, so on the whiteboard is most of the solution. Okay, and I'm just going to add, I guess, kind of the whole solution, but I'm just going to do the calculation for you. So of that double integral. So we have this double integral, and so we have from 0 to 1 minus y, and we have from 0 to 1 of 2xy plus 3/2 y squared. And so this is dx dy. Okay, so now you integrate this. So the outer integral is from 0 to 1. And so that's dy. But now inside we have that other integral from 1. We have the integral from 0 to 1 minus y of 2xy plus 3/2 y squared dx. And so you calculate this to find what's in the bracket there. And so an antiderivative of that would be x squared y plus 3/2 x y squared. And so you evaluate that. So you evaluate that from the lower limit, which is 0, to the upper limit, which is 1 minus y. And so you're plugging in for values of x because it's the x. And so if you plug in x equals 1 minus y, you get 1 minus y squared times y plus 3/2 x, which is 1 minus y times y squared. That's the value when x is 1 minus y. And you subtract the value when x is 0, which is you get 0. And so this is equal to this expression here. Okay, so now you have this expression here. Good. Okay, and so now you're integrating from 0 to 1 of that. Okay, and so you just want to find the value of that integral. And so now you want to find the value of that. So to do that, you can multiply out. So it's the integral from 0 to 1 dy. And so if you multiply out 1 minus y squared times y, you get 1 minus 2y plus y squared times y plus 3/2 times 1 minus y times y squared, which is y squared minus y cubed. And then this is equal to the integral from 0 to 1 dy of what's in there. So there's only a 1 there. There's, so you have times y there. So you have y minus 2y squared plus y cubed plus 3/2 y squared minus 3/2 y cubed. Good. Okay, and so now we have this. And so now there's some terms repeat. The y, there's only one y term. You have minus 2y squared plus 3/2 y squared, which is minus 1/2 y squared. Okay. Okay, so then the y cubed, you have 1 y cubed minus 3/2 y cubed, which is minus 1/2 y cubed. Okay, so now you have that integral, and you want to calculate that. And so you find an integrand of the integral, which is y squared over 2 minus y cubed divided by 6 minus y to the 4th divided by 8. You want to evaluate that from 0 to 1. And so that's equal to, you plug in 1 minus plugging in 0. So if you plug in 1, you get 1/2 minus 1/6 minus 1/8. If you plug in 0, you get 0. So then this is equal to their fractions. And so 8, 16, 24. So they have a common denominator, 24. This is 12 over 24 minus 4 over 24 minus 3 over 24. And so this is equal to 12 minus 7, which is 3 divided by 24, which is 1/8. Oh, wait. 12 minus 7 is 5. It's 5 over 24. Okay. That's it. Okay, and so that's 5 over 24. Okay, so all of this is the calculation of this integral here. Okay, so on the whiteboard, I showed you how you can express the solution to this problem as this double integral. And so here I'm just going into the long calculation of it. So the final answer is 5 over 24. Okay, so next is 7.2.4, which is on marginal distributions. So definition 7.4. Let x, y be discrete random variables with joint probability function f of x, y. The marginal probability functions of x and y, respectively, are given by f sub x of little x, which is equal to the sum over all possible values of y, little y, of f of x comma y. Okay, and note that f sub x of little x is equal to the probability that capital X is equal to little x, which is equal to little f of little x. Okay, f sub capital Y of little y is equal to the sum over all possible values of x little x of little f of x comma y. And note that f sub y of little y is equal to the probability that capital Y is equal to little y equals little f of little y. It's saying that the probability that capital Y is equal to little y is adding up all the f of x comma y over all possible values of little x. So if all the possible values of little x were 1, 2, and 3, you would want to know the probability of y when x is 1, probability of y when x is 2, and the probability of y when x is 3, and add those 3. And so you're exhausting all the possible values of y by going over all possible values of x and find the probability of f of x comma y for each possible value of x and adding. Okay, and so that's the meaning of that. Okay, B. Let x comma y be continuous random variables with joint probability density function f joint probability density function f of x comma y. The marginal probability density functions of x and y respectively are given by f sub capital X of x is equal to the integral from negative infinity, given by integral from negative infinity to infinity of f x comma y dy, which is equal to given by that and f sub y of y is equal to the integral from negative infinity to infinity of f of x comma y dx. Okay, so it's just like the discrete case, except when it's continuous, you're just integrating over all values of y to get f sub x of x, and integrating over all possible values of x to get f sub y. It's just infinitesimal sum instead of a discrete sum. Okay, and note that the probability that a is less than x less than b is equal to the probability that a is less than x less than b, and negative infinity is less than y less than infinity. So this is equal to the integral from negative infinity to infinity of the integral from a to b of f of x comma y dx dy, which is equal to integral from a to b of the integral from negative infinity to infinity. So you can switch limits of integration by what's called Fubini's theorem. So this is dy, and then dx. Okay. And this is equal to, you don't need to worry about what Fubini's theorem are justifying switching, but you can because you're dealing with a rectangle. Okay, and so then this is f sub x of little x dx. Okay, because this integral here with respect to y is f sub x of x. So the integrand of the outer integral is this integral, which is f sub x of x. Okay, and so this implies that probability that a is less than x less than b is equal to that integral. Okay, so example 7.14. Find the marginal probability density function of the random variable capital X of a previous example, example 7.5. Find the probability that X is greater than 2. Okay, so the joint probability density function that we care about from that example is this. It's f of x comma y is equal to the integral from 0 to infinity, but it's equal to e to negative x, e to negative y, for x positive, y positive, and 0 elsewhere. Okay, so that means that f sub capital X of x is equal to the integral from negative infinity to infinity of f of x comma y dy, which is equal to, okay, so there's two possibilities. So either you have the integral from 0 to infinity of e to negative x times e to negative y dy, which is equal to e to negative x. This is for x positive. Or you have 0 everywhere else. Okay, and so the probability that x is greater than 2 is equal to the integral from 2 to infinity of our f of x, dx, which is equal to this integral, where we found it to be e to the negative x, where x is positive. And so since x is from 2 to infinity, it's always positive there. So that means f of x is e to negative x there. And so this is equal to, when you calculate, it's e to negative 2, which is equal to approximately 0.1353. And that's the probability. Okay. Okay, so let's stop here. Okay, stay with me for just another minute here. Okay, so so that's it for class today. We'll have class again on Tuesday. So don't forget that the second exam is, the final is on December 21st from 6:15 p.m. to 8:15 p.m. The second exam is on December 9th. The review for the second exam is on December 7th. There's just a little bit more material and then we are done. So what I'm going to do is I'm going to post, when I assign the homework, I will also have the solutions, and I'll have a video going over the solution. Okay. And so after you do the homework after the last lesson, I'll have a video going over the homework. Okay. And so then all the material will be covered and the homework. Okay. So I'll see you next class on Tuesday. Yeah, the video will be posted on YouTube, but it'll be after the next lesson. So you'll still be talking to me during the next lesson. And so I'll be specific about it during that lesson. I'll tell you, it's, exactly, but it'll be on YouTube. Yeah, it'll be on YouTube. Okay, you're welcome. That way, all of the homework is covered. Okay, but we're almost done with everything. Very close to being done. Okay, so I'll see all of you next Tuesday. Have a good weekend. Bye.
I have a question.
Okay, yeah.
So are we going to have a final review for a final exam?
So the second exam is on the last day of class, December 9th, right? So, well, don't forget that we have an office hour. I announced that, right? So December 8th, right? So we have an office hour December 8th. So if you have questions about, the whiteboard notes, yeah. Okay, so let me save the whiteboard notes. So what I can do is I can help you with the final. Also, I can, after you have the test on the 9th, I teach a class afterwards. If you don't mind staying up late, I'm willing to have a very late at night session after my second class, after this class, in which I do a review. If you want that, if people would go to it, I'm willing to, after everything's done with my other class, I'm willing to have a review also. Okay.
Okay.
Or we could work something out. So I'm willing to find some time in that day to help you. I figure it's better after the third exam. So, yeah. Okay, so we can talk about that more on Tuesday. Okay.
Okay.
Okay, so have a good night. I have to go, but I'll see all of you next Tuesday.
Okay, thank you.
You're welcome.
Bye, Professor. Have a great weekend.
You too. Bye, everybody.